A molecular orbital diagram is the most accurate bonding theory that we have, so it's more accurate than the Lewis, and it's also more accurate than the valence bond theory with the hybrid orbitals. It does require a whole lot of calculations, but I'm not asking you to do any of those calculations. Everything that requires those calculations I'm going to always give you, and that's the order of the orbitals in the molecular diagram. So that can change, so always look here to see what order the orbitals go in. I'm just going to walk you through an example. Draw a molecular orbital diagram of the molecule nitrogen monoxide. Label all the orbitals and calculate the bond order. The order of the molecular orbitals from the p orbitals is sigma, pi star, sigma star. Okay, so the first thing you want to look for is, what am I drawing a molecular orbital of? In this case, it's nitrogen monoxide, so we have nitrogen and we have oxygen pairing together. First question is, which one of these is more electronegative? The more electronegative by convention goes on the right side. The oxygen is more electronegative. So I can start to arrange my molecular orbital diagram by putting nitrogen on the right and oxygen on the left. All of this is going to go on a scale of increasing energy. I will always put the atomic orbitals on the outside, so whatever two atoms we're combining, their individual atomic orbitals go on the outside, and then in the middle we'll put the molecular orbitals. So these atomic orbitals are going to be the same as what we did in chapter 7, where you were drawing orbital diagrams of the different atoms. This part is exactly the same as that. The only thing that's new is how those combine into molecular orbitals. So first, look for nitrogen on your periodic table and determine what its valence shell is. If that's a little bit tricky to do in your head, you can always write out its electron configuration. So nitrogen has an electron configuration of 1s2, 2s2, 2p3. The ones in the highest n will be our valence. Only the electrons in these orbitals will be involved in the bonding, so those are the only ones that we need to consider. We know that the s has a lower energy than the p, so here's an s orbital. We know that for the s sublevel, there's only one orbital for the sublevel. For a p, there's three ways to orient it, so there's three orbitals for that sublevel. For oxygen, you can do the same thing. Oxygen has an electron configuration of 1s2, 2s2, 2p4. So it's the same orbitals in the valence shell for oxygen, so we'll have the 2s and the 2p. Now the question says to make sure to label all the orbitals, so while we're doing those, let's just go ahead and label them. These are 2s and these are 2p. Those are just the valence shells. All right, now when you're making the molecular orbitals, I'm going to do that in blue, however many orbitals you combine, you need to have the same number of orbitals for the molecular orbital. This isn't always true, but for this class this will be true. The s orbitals will combine together and the p orbitals will combine separately. This can be a whole lot more complicated than we're talking, but we're going to keep it real simple. So if you have s orbitals here, these two will combine in the middle. I have 2 orbitals, so both of those will combine together in the middle to make 2 new orbitals, one at a lower energy and one at a higher energy than it originally was. Alright, so because we had 2 s orbitals, we have 2 new molecular orbitals, and we like to connect them with dotted lines just to show where they were coming from. In the p section, we have 3 orbitals here, we have 3 more over here, 3 plus 3 is 6, so we should have 6 orbitals in the middle, because these 3 plus 3 atomic orbitals combine to make 6 molecular orbitals. Now the trick is they combine in this order. Now a sigma bond is a head-on bond. Remember, these p orbitals have a shape like this. You have one shaped up and down, one shaped coming in and out of the page, and one going along the x-axis. Only the one along the x-axis can make a sigma bond. The ones going up and down, they can come up right alongside each other, but this is a pi bond, and the ones going in and out of the page are going to be similar to that, giving a pi bond. So if you have a sigma bond, there's only one way to arrange that, so the sigma will always just be one orbital. Okay, one for the sigma and one for the sigma star at the very top. And then you have 2 different ways that you can arrange the pi, right? So you will have 2 orbitals associated with that pi bond, and then 2 associated with a pi star. Make sure these go in the order listed in the question. I'll always tell you the order. So sigma goes on the bottom, so that's a single orbital. Sigma means single orbital. Pi means you have 2 orbitals. Pi star means you have two orbitals, but it has a higher energy than the original atomic orbitals. And the sigma star, one orbital, sigma is single, but has a higher energy than the original atomic energies. So at the end, you should have a total of 6, because that's how many p orbitals you started with. 3 of them should be below the energy of the original atomic orbitals, and 3 of them should be above. So this is a single bond here at the bottom, right here, so that means this is also a sigma, and because this is a single, it's still a sigma, and the one that has higher energy than the atomic orbitals that it came from will be an antibonding orbital, so a sigma star. Okay, so we've set up our diagram. We have labeled the orbitals. Okay, the next thing we need to do is actually put electrons into our diagram. So nitrogen, we said, had this electron configuration. We're only using the valence electrons, so we're going to put 5 electrons into our diagram. We will fill them up with the Aufbau principle, where we build up from the bottom. So we're going to fill up our s orbital with 2 before moving on to the next orbital, giving us 3 here in the p orbital. Let's do the same with oxygen. This time, though, we have 6 electrons to distribute, so we have 2 here, and then we have 4 here. However many electrons you have on the atomic orbitals, you put that same number into the middle. So I have 2 electrons here and 2 electrons here. That means I need to put 4 into the middle, into the molecular orbitals. So I can fill up from the bottom, 1, 2, 3, 4. Okay, so we put all of those electrons in. Remember, you can have a maximum of 2 electrons per orbital. When we move up to the p orbitals, we have 3 plus 4, so we need to put in 7 electrons. We'll move up from the bottom, 1, 2, 3, 4. If they're on the same energy level, spread them out before moving up. Okay, so 1, 2, 3, 4, 5, 6, and then our 7th will go up here. So this is a completed molecular orbital diagram for nitrogen monoxide. The last thing that we want to do is calculate the bond order. To calculate the bond order, we will use the equation that says the number of electrons in bonding orbitals minus the number of electrons in antibonding orbitals divided by 2. It takes 2 electrons to make a bond, so that's why we divide by 2. So we go over here and we look at how we labeled this. This is a bonding, these are bonding orbitals, and then anything with the star is an antibonding orbital. Count up all the electrons in our bonding orbitals, 1, 2, 3, 4, 5, 6, 7, 8, and we subtract from it the number in our antibonding orbitals, 1, 2, 3, and divide it by 2. So then we have a bonding order of 2.5. Anything above 0 means that you would be likely to find this. So having a bond order of 2.5 means that this is actually a quite stable molecule.